Section 14.4. The change of concentration with time. The rate laws that we've examined so far enable us to calculate the rate of a reaction from the rate constant and reactant concentrations. These rate laws are also converted into equations that show relationship between the concentrations of the reactants or the products in time. The mathematics required to accomplish this conversion involves calculus. We don't expect you to be able to perform the calculus operations. However, you should be able to use the resulting equations. We'll apply the conversion to two of the simple rate laws. Those of the first order overall and those of the second order overall. First order reactions. The first order reaction is one of whose rate depends on the concentration of the single reactant raised to the first power. For reaction of the type A yields products, the rate law may be the first order. Rate equals negative, since it's going away, delta concentration of A over time equals the K subconcentration of A. This form of the rate law, which expresses how the rate depends upon concentration, is called the differential rate law. Using an equation from calculus called the integration, this relationship can be transformed into an equation that relates the concentration of A to the start of the reaction, concentration of A at the beginning, to its concentration at any other time, T. So the natural log of concentration at any time over its initial concentration is equal to negative KT. This form of the law is called the integrated rate law. The function ln of the equation is called the natural logarithm. Equation 1412 can also be rearranged and rewritten as follows. The natural log of A to any time equals negative KT plus the natural log of the concentration of A at the initial. Equations 14.2 and 3 can be used with any concentration units as long as the units are the same for both A sub t and A sub 0. For a first order reaction, equations 14.12 and 13 can be used in several ways. Given any three of the following quantities, we can solve for the fourth, K, T, A sub 0, and A sub t. Thus, you can use these equations, for example, to determine the the concentration of a reactant remaining at any time after the reaction has started, or 2, the time required for a given reaction of a sample to react, or 3, the time required for the reactant concentration to fall to a certain level. Equation 14.13 can be used to verify whether a reaction is first order and to determine its rate constant. This equation has the form of a general equation for a straight line, y equals mx plus b, in which m is the slope and b is the y-intercept of the line. For a first-order reaction, therefore, a graph of the natural log of A sub t versus time gives a straight line with a slope of negative k and a y-intercept of the natural log of A sub 0. A reaction that is not in first order will not yield a straight line. As an example, consider the conversion of methoisonitrile to acetylnitrile. Because experiments show that the reaction is first order, we can rewrite the equation as the natural log of acetylnitrile equals negative Kt times the natural log of acetonitrile. Figure 14.7 shows how the pressure of methoisonitrile varies with time as it rearranges in the gas phase at 198.9 Celsius. We can use pressure as a unit of concentration for a gas because from the ideal gas law, the pressure is directly proportional to the number of moles per unit volume. Figure 14.7b shows a plot of the natural logarithm of the pressure versus time, a plot that yields a straight line. The slope of this line is negative 5.1 times 10 to the negative 5 to the seconds. You should verify this for yourself. remembering that for your result may slightly vary from ours because inaccuracy associated with reading the graph. Because the slope of the line equals negative k, the rate constant for this reaction equals 5.1 times 10 to the negative 5 per second. Second order reactions. A second order reaction is one whose rate depends on the reactant concentration raised to the second power, or on the concentration of two different reactions, each raised to the first power. For simplicity, let's consider reactions of the type A yields to products, or A plus B equals products, that are second order in just one reaction, A. So the rate equals negative change in the concentration of A per time equals K sum A to the squared. With the use of calculus, the differential rate law can be used to derive the following integrated rate law. 1 over A sub t equals kt plus 1 over A sub 0. This equation, like 1413, has four variables, kt, A sub 0, and at, and any one of these can be calculated knowing the other three. Equation 1414 also has the form of a straight line, y equals mx plus b. If the reaction is second order, a plot of 1 over A sub t versus t will yield a straight line with a slope equal to k and a y-intercept equal to 1 over A sub naught. One way to distinguish between first and second order rate law is to graph both the natural log of A sub t and 1 over the concentration of A sub t against t. If the natural log of A is linear, the reaction is first order. If the 1 over the concentration of A sub t is linear, the reaction is second order. Half-life. The half-life of a reaction, T to the 1/2, is the time required for the concentration of a reactant to reach 1/2 of its initial value. The concentration of T to the 1/2 equals 1/2 A to 0. The half-life is a convenient way to describe how fast a reaction occurs, especially if it's a first-order process. A fast reaction will have a short half-life. If we determine the half-life of the first-order reaction by substituting A to the T 1/2 into equation 1412, the natural log of 1/2 of AT sub 0 over A sub t 0 equals negative KT to the 1/2. The natural log of 1/2 equals negative KT to the 1/2. T to the 1/2 equals negative natural log of 1/2 over K equals 0.693 over K. From equation 1415, we see that T to the 1/2 for a first-order rate does not depend on the starting concentration. Consequently, half-life remains constant throughout the reaction. If, for example, the concentration of the reactant is 0.12 molar at some moment in the reaction, it will be just 1/2 of that after one half-life. After one or more half-life passes, the concentration will drop to 0.03 molar, and so on. Equation 1415 also indicates how that we can calculate the T to the 1/2 for a first-order reaction if K is known, or if T to the 1/2 is known. The change in concentration time for the first-order reaction, rearrangement of methyl isonitrile at 198.9 Celsius, is graphed in figure 14.9. The first half-life shown is that at 13,600 seconds, that is 3.78 hours. At a time of 13,600 seconds later, the isonitrile concentration is decreased to 1/2 of 1/2, or 1/4 of the original concentration. In a first-order reaction, the concentration of the reactant decreases by 1/2 in each of the series of regularly spaced time intervals, namely T equals 1/2. The concept of half-life is widely used in describing radioactive decay, a first-order process that we'll discuss in detail in section 21.4.